in chapter 15, we have talked a lot already about how to find the area underneath a curve, right? We started off by estimating using rectangles with either left endpoints or right endpoints, or even I think we did a few midpoints where we can estimate the area underneath the curve using a couple different rectangles. But then we talked about how we can find the exact area underneath the curve where we can actually integrate. We can integrate our function from a to b, and that'll give us the exact area underneath that curve. We talked about that being the definite integral. We evaluated it using our fundamental theorem of calculus. But what happens if I asked you to find the area in between two curves now? So instead of just the area underneath one curve, what if I asked you to find the area in between two curves? So let's say you have a function f, and you have another function g, and we want to find the area in between those two functions. Well, I could take the area underneath f, I can take the area underneath g, and if I subtract the area of f from the area of g, doesn't that give me the area in between? I can take the whole minus g, and that'll give me the area in between. So anytime we're looking to find the area in between two functions, we can take the integral of the top minus the bottom from a to b. So we're going to integrate top minus bottom, and that'll give us the area in between those two curves, right? Okay, now in our picture, f was always at the top and g was always underneath. So it was kind of easy to figure out which one was the quote-unquote top function and which one was the bottom function. But if our curves kind of intersect and change, my functions might be different depending on where I'm at in my graph. One might be on top and then all of a sudden change to the bottom, or vice versa, right? And so what we have to do anytime we're being asked to find the area in between two functions, we've got to follow a couple different steps. We have to first figure out where these functions intersect. We want to figure out where they cross. We can figure out where they intersect or cross by setting the equations equal to each other. We then have to figure out which function is at the top versus which one is at the bottom in each of these different intervals by plugging numbers in and seeing which one is bigger. That will tell us which one's on top versus which one is on bottom. And then we'll need to set up maybe a couple of different integrals to integrate top minus bottom. Let me show you an example. If you look at the picture that I've drawn here, we have the blue function f, we have the red function g. You notice that they intersect at x equals 2 and x equals 10. And if I were asking you to find me the area in between these two curves from 1 to 12, you might notice that I have a section here between 1 and 2. And which function is at the top in this interval? It looks like g is at the top, right? So I would integrate, and I would do g minus f, top minus bottom, from 1 to 2. The problem is, at 2 they intersect, don't they? And from 2 to 10, their other intersection point, which function is at the top? This time, f is at the top. So then I would have to set up another integral, integrating from 2 to 10, with f being the top function. So I would want to do f minus g in that interval. And then again, they intersect at 10. And if I was finding the area between 10 and 12, I would want to make sure that I integrated from 10 to 12. But this time, my new top function is again g. So I would do g minus f, top minus bottom. So I had to first figure out where they intersected. I then had to figure out which one is top versus bottom so that I can set up a couple different integrals. On this one, I would have 3. I would have one from 1 to 2. I would have one from 2 to 10. And then I would have another one from 10 to 12 so that I can get all the way from 1 to 12. Remember, in the interval from 1 to 2, the top function was g, so I'd have to do g minus f to get the area in between. In between 2 and 10, my top function was f, so I'd have to do f minus g to get the area in between. And then from 10 to 12, my top function changed again so that it was g minus f. So find the intersections, figure out which function is on top versus the bottom in each of those intervals, and then set up as many integrals as you need to in order to find the area in between our two functions. Let's do another example with actual equations here. If you look at example number 1 with me, it asks us to find the area bounded by the function f of x if it's negative x squared plus 1, g of x, if we have g of x as 2x plus 4, the line x equals -1, and the line x equals 2. I don't know about you, but it's much easier for me to draw a picture and hopefully visualize what's happening so I have an idea of what's going on. I know that f of x was a quadratic. It was a parabola, right? And x squared plus 1 is a parabola. It's a parabola that opens down because my leading coefficient is negative. And if I have a plus 1 behind it, I know that it's a parabola that's shifted up 1 and facing down. So that's how I kind of sketched my graph of f. Then I'm looking at g. G looks like it's an equation of a line, doesn't it? A y equals mx plus b. It looks like it has a y-intercept of positive 4 and a slope of positive 2, up 2 over 1. So that's how I kind of drew the sketch of g. So I have my parabola f, I have my line g, and then I also have two other lines. At x equals -1, that means it's going to touch the x-axis at -1 and be a vertical line. I also have another line, x equals 2, so it's going to touch the x at 2 and be a vertical line. So you might notice in my picture that the area bounded by these four things is that pink shaded section. I want to find that area of that pink section. If I want to find the exact area, we know that we have to integrate, right? But we have to have a starting point and an ending point so we know where to integrate from. What is our a and our b, our limits of integration? If we're finding the area between two functions, or in this case, all four functions, right? What we need to do is figure out who's on top and who's on bottom. Remember our 3 steps though. We first have to figure out where they intersect. We have to figure out which functions are top versus our bottom in each interval, and then we've got to set up different integrals. If you look at our picture though, because we've kind of drawn our picture and we have a good visualization of what it looks like, you might notice that G and F, they don't intersect in the area that we're talking about. And so my functions don't intersect. If they don't intersect, how am I supposed to know where to start and where to end, what my a and b are going to be? Well, you might notice that's why they gave us the x equals -1 and the x equals 2. So now I know exactly where I want to start on the x, I know exactly where I want to end on the x, and then I just want to find the area in between, this little shaded part, right? So I actually know that my 2 starting and ending points are going to be from -1 to 2. So that's where my integral is going to be, my limits of integration, from -1 to 2. If you weren't sure, what you could always do is take g, take f, and set those functions equal to each other. When I did that, I noticed that I had a quadratic, and I moved everything to the same side. I then tried to factor, or use quadratic formula, and I realized that I was going to have imaginary solutions, meaning they're not going to intersect. But if they did intersect, and they intersected in that shaded area that we were talking about, then that would help us figure out what integrals we would have to set up depending on the different times that they intersect and who's on top and who's on bottom. But because I had this picture, I could see that they didn't intersect. I did some algebra to verify that they weren't going to intersect. And so I know that I'm going to start at x equals -1. I want to go all the way to x equals 2. And I want to find the area in between these two curves. That means I want to do top minus bottom. We can see in our picture that g is always going to be the top function. If you weren't sure, what you could do is plug in a number in that interval from -1 to 2 into the f function and into the g function and see which y value, which output is higher. Test a number. I don't know, maybe 0. If you plug in 0 to f, 0 squared is 0, and 0 plus 1 is 1. If I plug in a 0 into g, 2 times 0 is 0, and 0 plus 4 is 4. That means g is 4, and f is 1 at x equals 0, and that means that g is higher. 4 is higher than 1, right? So I know that g is higher than f, and it's going to be our top function. So that's going to help me set up my interval, where I can integrate it from, remember, -1 to 2 of my top function minus my bottom function. You might notice that I put parentheses because I need to make sure that I'm careful and I distribute the negative through that second parenthesis. I'm going to distribute the negative. I'm going to combine like terms. And I now have an integral that says I want to integrate from -1 to 2 of the function x squared plus 2x plus 3. This is going to help me find the area in between these two curves from -1 to 2. All right, let's actually integrate it. I got an x cubed over 3 plus a 2x squared over 2 plus a 3x, and I want to evaluate it from -1 to 2. Using our fundamental theorem of calculus, we want to plug in our upper limit. We want to plug in that 2, and then we want to plug in our lower limit, the -1, and then we want to subtract. Using my calculator, if we need to, I can plug in 2 and evaluate, and I got 38 over 3 for that first set of parentheses. Using my calculator again, I want to evaluate, and I ended up getting -7/3 for the second part of my parentheses when I evaluated at -1. I'm going to subtract these two values, so you might notice that these two negatives turn into a positive, and I ended up getting the exact area in between these 4 lines between the curves G and F from -1 to 2 is 15. All right, so you can see an exact picture, not my ugly sketch, looks something like this. But it was very helpful for us to sketch it first so we can see where the area is. We could see that the two functions didn't intersect. We know where we were starting and where we were ending, and where our top minus our bottom function was going to be. And then we can integrate it for top minus bottom.